Last day, we really looked into the field of organic chemistry, and we did a lot of review of Science 9 and Science 10 concepts. What I want to do is take a few moments and just make sure that we are starting with that information relatively fresh in our brains and see if you have any more questions. Question number 1. You need to be able to identify an organic compound. Sometimes it's easier to identify what is not an organic compound. Question 1A and B are both organic compounds. How do you know? So all of them are going to have carbon in these examples. So A, B, C, and D all have carbon. But I could do HCN and that would still be inorganic. Okay, so remember what I said. Sometimes it's easier to identify why it's not an inorganic. So if it ends in the word oxide, no. If it is an ionic compound, inorganic compound. If you have a metal in there, that is your red herring, that it is an inorganic compound. If you look at the formula C6H12O6, that's from Science 10. Do you remember what C6H12O6 is? We talked about it when we studied photosynthesis.
Oh, it's glucose or whatever? Yeah, glucose.
Pardon? Glucose.
There you go.
That doesn't end in oxide. The name is glucose. There is no metal in C6H12O6. It is an organic substance. C3H8. Oh, if we are to name this organic compound, what would the word for 3 be? So in organic chemistry, propane. C3H8 is actually propane, the stuff you use in your barbecues. It definitely does not have a metal in it. It does not end in oxide. There's no O's in there at all, so there's no way that this could be something oxide. It is an organic compound. C, it has carbon in it, but it is inorganic. How do you know? How do you know that NaCN, sodium cyanide, is an inorganic compound? How do you know that sodium cyanide, 1C, is inorganic? The metal is the clue. Sodium is a metal. Same thing with calcium in question D. Because both are ionic compounds, that automatically makes them inorganic compounds. 2 unique characteristics of carbon make it the parent of organic chemistry. Some people say the father of organic chemistry, but that really isn't fair because atoms are not gender specific. That's why I changed the word to parent. The 2 characteristics that make carbon the parent of organic chemistry is the fact that it can form 4 bonds with something else. We call that tetravalent. And it is able to combine with itself. The fancy word for that is catenation. How did you do with drawing a Bohr model of sulfur? So sulfur is number 16 That means it has 16 protons and 16 electrons. When we draw Lewis dot diagrams, we are only drawing dots for the electrons in the last energy level. The Bohr model, the Lewis dot diagram should only have 6 dots. Place 1 on each side before you double up. So you should have 2 pairs of what we call paired electrons and 2 electrons by themselves. How many places can sulfur bond? 2. That is its bonding capacity. How many electrons would it have to share with something else? 2. So it would have to share this electron and this electron with something else to form that covalent bond. A covalent bond is when you share electrons between 2 substances. Questions? Today we are going to apply the octet rule and practice drawing molecules. I'm trying to teach. Today we're going to apply the octet rule and draw molecules to show the sharing of electrons. The octet rule states that there needs to be 8 valence electrons, or 8 electrons around a substance. When you draw a formula for something, the substance that is first in the compound formula is the center of the molecule. Start by drawing the Lewis dot diagram for that substance. Please turn to the second page in your worksheet booklet. The first molecule that we're going to practice is OCl2. Please start off by drawing oxygen and the dots, the Lewis dot structure for oxygen. Oxygen is in group 6A, therefore it is going to have 6 valence electrons. Where the 2 lone electrons are the places that oxygen can connect with something else, in this case chlorine. Because you are writing or printing with one color, what you might want to do is, instead of placing dots, put crosses. That's why these structures are sometimes called the dot and cross model. For example, chlorine has 7 valence electrons. Instead of placing dots, you might want to do crosses, so that you can differentiate between the electrons of the chlorine and the electrons of the oxygen. Because I have the ability to swap out colors, I will often just change the color of dots. There are 2 atoms of chlorine. I'm going to place my electrons so that the lone electron of chlorine is by the lone electron of oxygen. Because what is going to happen is this electron is going to be shared with oxygen, and oxygen is going to share this electron with chlorine. Similar to here, oxygen is going to share this electron with chlorine. Chlorine is going to share its lone electron with oxygen. This is the Lewis dot structure. You will also see this molecule drawn like this. Sometimes you will have a sphere. So we're going to be working with atom kits. So you'll have spheres with the element symbol. And that's called a ball and stick model. Right now, when we draw our ball and stick models, we're not going to worry about valence electrons yet. They will eventually become important when we predict bond angles. So bond angles are how far apart these things are going to be. One step at a time. Give O2 a try. Both oxygen atoms have 6 valence electrons. Both oxygens are going to share both electrons that are by themselves. We have 2 sets of electrons that are being shared. For each pair of electrons that are being shared, we show one bond or line. Each line is equivalent to 2 electrons being shared. Because there are 2 lines between oxygen atoms, we refer to this as a double bond. Try question 3. We have 2 phosphorus atoms and 3 oxygen atoms. Keep in mind the octet rule says that each atom must have 8 valence electrons. See if you can figure out the connections. So one pair of electrons is going to definitely be shared between the two phosphorus. I'm going to connect this one here. So now I have 2, 4, 6, 7. Oh, we can do a number of things if you want. You can connect this one, and then you have 2, 4, 6, 8 electrons around the phosphorus. Each oxygen has 2, 4, 6, 7. 2, 4, 6, 7. So if they shared these two electrons, that would give them 2, 4, 6, 8. 2, 4, 6, 8. We can make a connection here, and then we have 2, 4, 6, 7, and a connection here, 2, 4, 6, 8, 2, 4, 6, 8. Megan came up with a different one than I did, and that's totally fine. As long as each one of those atoms has 8 electrons connected to it, it is totally fine to come up with another structure. If you come up with another structure with the same formula, it's called an isomer. Iso in science means same or similar. Mer means parts. So both of our diagrams use 2 phosphorus and 3 oxygen, but we arranged our electron pairs differently, which means the 3-dimensional structure is going to be slightly different, and that's fine. You have all sorts of types of isomers with organic chemistry, which is one of the reasons why we have so many organic molecules. Next structure, we have our first chain, C3. Put the 3 carbons side by side in a chain. That's the only hint I'm going to give you. Okay, I'm just going to say this one more time just so that Christian gets it, okay? All right, so Christian, each carbon has 2, 4, 6, 8 electrons. Hydrogen is an exclusion to the octet rule because there's only 2 electrons that can go into the first energy level. There's no way that hydrogen can take on 8 valence electrons. Here is the model for this. Carbons on the end usually have 3 hydrogens connected, versus the internal carbons have 2. There is another way that you'll see hydrocarbons written. It drives me crazy personally, but I do want to show it to you. This molecule could be written in this way.
That's so easy though.
Yes and no. If you understand why there's 3 hydrogen connected to the carbon, yes. So you have to have an understanding of the octet rule and molecular structure to understand why they come up with that line here. I like this model a little bit better because then I can see the lines and I can quickly look at this and I can count lines. Each line represents 2 electrons being shared. So I know that if there's 4 lines, coming from carbon, that's going to fulfill the octet rule because each of these is 2 electrons. So I can quickly look at this structure and verify if it has the correct number of electrons. With this one, it's like I kind of have to do the picture in my head back to here anyway. Try number 5. cyclic structure was proposed for C6H12. There is another structure. If I do it like this, can you see what the other structure might be like? So we have a bond shared here, 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 here. Gets a little bit messy when you do the circles. So this carbon has 2, 4, 6, 7 electrons. This carbon has 2, 4, 6, 7 electrons. Can share another set of electrons between carbons. So you get a structure with a double bond somewhere in there. This double bond could be here, or this double bond could be here. There's multiple places where it could be. So that's how we use those dot diagrams to determine electron pair sharing and do the basis of drawing molecules. How do you feel about this stuff so far? Yeah. Well, we'll be doing lots of drawing throughout this unit. Lots of drawing. So we're going to start off with probably one of the simplest categories of molecules, which is going to be the aliphatic hydrocarbons. The word hydrocarbon gives you a clue about what all of these compounds are made up of. Hydro, hydrogen, and carbon literally means carbon. We're going to focus on straight chains for now. So if I just take one moment, I'll come back to the slide. This is what we would call an aliphatic hydrocarbon because it's a straight line of carbons. This is not an aliphatic. This is a cyclic compound. We're not going to talk about these quite yet. We will, don't worry. We have 3 types of hydrocarbons that we're going to talk about. Alkanes, alkenes, and alkynes. Alkanes are saturated. What that means is that the carbon has the maximum number of hydrogen possible in its structure. There is no other way to add more hydrogen to this molecule. Alkenes and alkynes are unsaturated. That means that there is a double or triple bond present. Alkenes have double bonds. Alkynes have a triple bond. They are unsaturated because if I break this double bond, I can add another hydrogen to each carbon. If I break this triple bond, I can add 4 more hydrogen to that. Where have we talked about saturated and unsaturated in the past? Health Science 20.
Good times.
So, in Health Science 20, we talked about saturated fatty acids, monounsaturated fatty acids, and polyunsaturated fats. So, a saturated fatty acid is all single bond carbons can be very, very long carbon chains. A monounsaturated fatty acid has one double bond somewhere in that structure. A polyunsaturated fatty acid has multiple double bonds throughout the structure. Do you remember which one's healthier for us? Saturated or unsaturated fats? Which one's healthier? Unsaturated. It takes more energy for the body to break those double bonds and use that fatty acid than to use a saturated fat. What's the best source of unsaturated fatty acids?
Yeah, I can tell you a lot of facts about the ball system if you want, but I cannot answer.
The source of saturated fats is animal-based products. Unsaturated fats are oil-based products that come from plants. So if you're ever told by the doctor that you have to reduce your triglyceride levels in your blood, you need to swap out the butter for margarine because margarine is made up of oils. Have you ever noticed on a margarine container, it says it's partially hydrogenated? Hydrogenation is when you add hydrogen. If you hydrogenate something, you break a double bond, and literally you have hydrogen being bubbled into this large vat of oil at a high temperature. And you start breaking a double bond and adding hydrogen. Why would we want to partially hydrogenate and make margarine? Margarine is made up of plant oils.
So it tastes better. I don't know.
Well, taste, it's more about texture. Do you want to take vegetable oil and pour it on your toast?
Yes.
Maybe if it's like a really nice olive oil, you take a piece of French bread and dip it in the olive oil or focaccia. But you don't usually crack open the bottle of canola oil, make a piece of toast, and then pour you some vegetable oil, right? We partially hydrogenate vegetable oils because saturated fats are solid at room temperature, and we like to spread things on our toast. Partial hydrogenation changes the state of margarine. Okay, I have to switch over to this video on my. This prefix chart is used for the number of carbons. It is found on page 4 of your yellow data booklets. The number of carbons in the chain becomes the first part of the word. Alkanes can be recognized by their name ending. So if you see anything with an ANE ending, that is a hint that it is an alkane. So we have our first slide here. Which one of these are alkanes? name ending A and E. A is an alkane. D is an alkane. And E is an alkane. How many carbons are going to be in methane? 1. The prefix for 1 is meth. How many carbons are going to be in the structure bute? 4. How many carbons are going to be in the structure prop? Nope. 3. So you need to refer to your prefix chart. Try not to guess, because you might not always be correct.